Moons literally come in a variety of shapes and sizes. And there are also many variations in their composition and origins as well. Now, to clear the air briefly about our nearest moon, we have our own moon, which we learned about in previous videos, and Mars has two moons, which may turn out to be captured asteroids. So we're going to save our discussion of Mars's moons later on when we talk about asteroids. But if we turn our attention back to the rest of the moons, there is a huge variety to select from. But first of all, let's just think briefly about what it is to be a moon. How do we define a moon? Well, simply stated, a moon is simply a natural satellite that orbits a planet or a minor planet. So that begs the first question, what exactly is a minor planet? Well, a minor planet is defined as any object that directly orbits the sun, but is otherwise not a proper planet or a comet. So we're talking about things like asteroids and Kuiper Belt objects and some other stuff that we're going to talk about later. So if a moon is going around something and that something is a planet or a minor planet, then it's a moon. But moons come in two main flavors. First of all, there are moons that have forward or prograde orbits. In other words, they move in the same direction as their host planet rotates. They're relatively large and massive, and they probably formed with their planet. These are called regular moons. However, if you zoom out from, let's say, Jupiter, you discover there are several more of these so-called irregular moons. These are moons that are often characterized as having retrograde orbits. In other words, they often revolve around the planet in an opposite direction of the planet's rotation. They're also relatively low in mass. They're kind of small objects, which really suggests that these are just captured asteroids. They didn't form with their planets, they formed elsewhere and were picked up at some point when they flew too close to the planet. So the moons that we see here are mostly the moons of the outer solar system. Let's just take a very brief look at some of them. Jupiter has 67 moons, and if you look along the top of your screen, you'll see a scale image of Jupiter, and its moons are drawn at a different scale, but their distances are laid out according to scale. So there are kind of two scales at work here. But at the bottom, we see there's a nice selection of several of these moons. So we have the four main satellites of Jupiter that were discovered by Galileo in 1610. And then you see some of these irregular moons that are just kind of these tiny little rocks that were just picked up along the way. If we look at Saturn, we notice that we have a similar variety, but its largest moon, Titan, actually has an atmosphere. Now that's kind of interesting because that was for a long time the first and only moon that we knew of that had an atmosphere. It turns out, however, that Enceladus, while it may not have an atmosphere, sports that little blue plume that you see, and those plumes, as we will later on learn, are geysers of water. So there's some very interesting stuff going on some of these moons. Uranus has 27 moons, and you may recall from a previous video that Uranus is knocked over on its side. It has an obliquity of 98 degrees. However, this means that not only is Uranus rotating at 98 degrees, but its rings and its moons are also orbiting in that same knocked over plane. So the entire Uranian system is knocked over as well. Now, Neptune has 14 moons. And by the way, all of these are just counts of the moons that we know of. There may be others that we have yet to discover, and nobody would be terribly surprised if we did find additional moons around these planets. Now, its largest moon is Triton. However, Triton is the largest example of an irregular moon. If you look at this image made by the Hubble Space Telescope, you'll see Neptune rotating from left to right, while Triton revolves around Neptune from right to left. So this is an example of an object that was formed elsewhere, probably in the outer solar system, well past the orbit of Neptune, and was later captured into a new orbit around Neptune at some point in the past. Let's examine the Galilean satellites of Jupiter. These four moons are Jupiter's largest moons, and they all share a common backstory. Namely, they all formed when Jupiter was forming. So you can imagine this as a kind of a miniature solar system. When we look at Callisto, what we find is that It is truly remarkable in the sense that it is remarkably unremarkable. First of all, we have a very heavily cratered surface. It's also a crust of mostly solid rock and ice. So, with all of these craters, that tells us that this surface is pretty old. It doesn't look like there's been any activity that has erased very many of these craters. Something else about Callisto is that it's about the same size as Mercury, and yet it is much less massive. Therefore, its density is much less. Now, we learned previously that Mercury is the second densest planet next to Earth. So, Mercury, therefore, must have an iron core with a thin mantle of rock and a crusty layer of silicates and rock. However, Callisto is the same size as Mercury and yet much less massive. Therefore, we think that its interior is really undifferentiated. In other words, Callisto formed but never differentiated, never got hot enough to melt and let the dense material sink to the core. And what we're left with is essentially a ball of rock, ice, and water. There may be a thin layer in there where the water may be liquid, but otherwise, Callisto is a geologically stillborn world. But this gives us a bit of a baseline to compare the other moons of Jupiter to. Let's go to Ganymede. Now, Ganymede is the largest moon in the solar system, and as you may be able to tell, it has far fewer craters. So this suggests a younger surface. However, while we do have these darker regions, which suggest that there was some paving away of the surface, it does not appear that there's been any recent geological activity. So with crater counts indicating a surface of about 2 to 3 billion years, that tells us that Ganymede was once geologically active, but no longer is. However, Ganymede has a magnetic field, and we know it has a magnetic field because we've seen aurorae around Ganymede. What you're looking at here is a composite image made by the Hubble Space Telescope. We have a visible light image of Ganymede, but then superimposed on it is an ultraviolet image indicating the presence of aurorae. These are highly charged particles reacting in Ganymede's magnetosphere, much like the aurorae do here on Earth and the aurorae around Jupiter itself. So this tells us that Ganymede's interior must be differentiated. So there's a crust of ice, followed by perhaps a thin saltwater ocean, followed by a mantle of essentially ice, followed by rock, and then an iron core. Perhaps there's a liquid iron core surrounding an inner solid iron core, thus providing the magnetic field of Ganymede. So we know that Ganymede was once geologically active, and in fact, it may still be geologically active every now and again. We just don't yet have enough information to conclude positively one way or the other. But now let's take a look at Europa. Europa is perhaps the most fascinating of the moons of Jupiter, and in fact, one of the most fascinating moons in the entire solar system. Just one quick look at Europa, and you notice that there is an utter lack of craters. There's a rather large crater in the lower right. It has its own ejecta blanket, and it has its own ejecta rays, but very few, if any, craters can be seen anywhere else. But what we do see, however, are cracks. These cracks are all over the moon of Europa. They are carving up or chunking up the surface into these kind of like wraps, and they're almost behaving like tectonic plates do here on the surface of Earth, except that rather than plates of crust and rock and silica and all kinds of stuff that we have here on Earth, we have plates of ice, and they are moving around, sloshing into one another, breaking apart, separating away, undergoing all of the same tectonic processes that we have here on Earth. Now that's a remarkable observation because this tells us that there has to be a source of internal heat to Europa that's driving all this tectonic activity. And as a matter of fact, when the Hubble Space Telescope examined Europa in ultraviolet light, so we're taking an image of Europa made by the Galileo spacecraft when it flew by in the 1990s, and we're superimposing it on top of an ultraviolet image of Europa made with the Hubble Space Telescope. Take a look down here. These blots of light may very well be water. They may be plumes of water being ejected from inside Europa. And so all of this is evidence that Europa not only has these plumes or these geysers of water, but that there must be an ocean of water, heated and warmed by the moon's interior, capped over by a layer of ice. And so the question isn't whether or not Europa has an ocean. The answer is almost certainly yes. What we really would like to understand is, what is that ocean like? Is it pure liquid all the way through, or is it very icy until it gets relatively close to the mantle, at which point the heat takes over? We just don't know. So really the main question is, how deep is Europa's ocean? The second question is, if you have a source of carbon and you have a source of energy and you have water, you certainly have all the ingredients you need for life. Could there be little Europa fishes swimming around down there? Hopefully one day we'll get to find out. So now we could take a look at the final and closest moon to Jupiter, Io. If Europa was a frozen paradise, Io is a volcanic mess. It is just one great big volcano of a moon. In fact, all of these circular patterns that you see on Io, these are not craters at all. These are volcanoes. Io has almost no craters whatsoever. Everything is a volcano on Io. As a matter of fact, these volcanoes have been imaged by the Galileo spacecraft when it was flying around the Jupiter system in the 1990s. And volcanoes were even spotted by the New Horizons spacecraft as it flew past Jupiter on its way to Pluto. So these volcanoes are very common. And yet, there's a bit of a question here. Why should a moon that is so small as Io have any heat left over? After all, any object this small should have radiated its heat out a long time ago. So why is there any heat in Io, let alone volcanoes? Well, the answer is due to the fact that Io's orbit is not a perfect circle around Jupiter. Now, I've drawn this illustration obviously not to scale, and I've really exaggerated the eccentricity of Io's orbit. However, this helps us to understand how the tidal forces come into play. If Io is at its farthest point from Jupiter, a position known as apogee, then the tidal forces exerted by Jupiter on Io are their weakest. In other words, Io is its normal shape and not really experiencing any tidal distortions. However, when Io comes to its closest approach, or perigee, then the tidal forces are the strongest. So strong, in fact, that it actually kind of squeezes Io and stretches it out a little bit. So this adds something called mechanical heat to Io's interior. And you can do this experiment yourself. You could take, for example, a paperclip. If you just hold a paperclip in your hand and just touch it with your finger, you'll get an idea of its temperature. However, if you take the paperclip and unfold it, and then just bend it back and forth a few times, touch it again, and you will definitely notice it is quite a bit hotter. So as Io is being squeezed and relaxed and squeezed and relaxed, that keeps its interior agitated, thus producing the volcanoes. However, there's just one other question. Why is Io's orbit elliptical? After all, under these tidal forces, Io's orbit should have been circularized by Jupiter a long time ago, and therefore there wouldn't have to be any tidal heating. However, Io is not the only player. Every time Io completes 2 orbits, Europa completes 1 orbit. And every time Io completes 4 orbits, Ganymede completes 1 orbit. This regular meeting up with the outside moons of Jupiter is called an orbital resonance. And this allows Io to experience a routine gravitational tug at regular intervals, courtesy of Europa and Ganymede. And this is what pulls Io out of its perfectly circular orbit. So Io maintains a slightly elliptical orbit, which allows Jupiter to tidally heat its interior, thus producing all the volcanoes that we see here. And those are the Galilean satellites of Jupiter, each one a world unto itself, each with a common backstory, and yet each one with a very different story today. Now, Titan is Saturn's largest moon, and in fact, it's the second largest moon in the solar system, next to Ganymede. But Titan is the first moon that we've encountered that has its own atmosphere. And we can't really see Titan's surface because its atmosphere is so thick. It's a smog dominated by nitrogen and methane. And as a result, we have no way of actually seeing through to the ground, at least not in the visible portion of the spectrum. If we switch to the infrared part of the spectrum, we can begin to make out some of the surface details, and we can get some idea of the surface lying underneath. So when we look at Titan's atmosphere, we find that it's about 19% more massive than Earth's. So Titan actually has a lot of atmosphere, but only through infrared can we start to make out the different layers in the atmosphere and the surface underneath. However, we actually got to see the surface for ourselves courtesy of a tiny probe called Huygens. In 2005, the Cassini spacecraft launched the Huygens probe down to Titan, and as Huygens entered into Titan's atmosphere, all we could see here is the hydrocarbon haze, but then it got through that haze layer, revealing the surface below for the first time, and when it finally landed, it found this, pebbles. But these are not pebbles of rock, these are pebbles of water ice. As a matter of fact, they're kind of rounded and smooth. This is not a result of a fuzzy picture. This is the result of the fact that these pebbles have been under, well, not underwater, but under a liquid methane. In other words, the temperatures of Titan are extremely cold. At minus 180 degrees Celsius, water will just freeze as hard as solid rock does on Earth. But methane, however, can exist as a liquid at these temperatures. So what we have are a dried up lake bed that used to be filled with liquid methane. And there's additional evidence for lakes on Titan. We see what's called specular reflection. This is the same phenomena as if you were flying in an airplane over a body of water. On a sunny day, then the sunlight strikes the water and hits your eyes at just the right angle, and it's a really blinding beam of intense sunlight coming at you. Well, that's specular reflection, and we can't see that at the visible part of the spectrum, but if we switch to infrared, yeah, we see specular reflection all the time, glinting off these lakes. When we look at Titan's surface with radar, we find these flat areas where no signal is returned. And these flat areas, colored in blue in the image on your right, are the outlines of lakes. So these are hydrocarbon lakes of methane, acetylene, and so forth. But there is a mystery here. You see, all of the hydrocarbons, particularly the methane, should be broken up by the sunlight. Now, even though the sunlight at Saturn is relatively weak, even at its low intensity, it's still enough to boil away or what's called photodissociate the methane. So the skies around Titan should be relatively clear. Why then is there all this methane in Titan's atmosphere? It's possible, although we don't yet fully understand, it is possible that Titan may still have active geology. There may be an active interior, possibly a source of heat, perhaps tidal heating from Saturn itself, that allows Titan to have a slightly differentiated interior and maybe even a very thin ocean underneath its icy crust as well. And so, if there's water and if there's energy from internal heat and there's plenty of carbon to go around on Titan, then it's possible that life may exist on Titan as well. Kind of amazing to think about it, since the part that you and I would walk around on is so poisonous and deadly to human beings, it may be suitable to little kinds of Titan fish. Now, Triton is Neptune's largest moon, but it's also the solar system's largest irregular moon. In other words, it most likely formed way out past the orbit of Neptune in what's called the Kuiper Belt and was later captured by Neptune's gravity. It's covered in ice, and in fact, it's a very bright surface because most of what we see on Triton is water ice and methane ice and some frozen CO2. And this makes Triton very bright. It has what's called a high albedo value of 0.76. To explain that number, if you'd imagine the darkest, blackest object in the world, that would be an albedo of 0. And if there was something that could reflect 100% of the light shown upon it, that would be an albedo of 1. So this is reflecting about 76% of the light shining on it. That's a very bright object. But that also means that sunlight doesn't really warm Triton up very much. This makes Triton the coldest world that we know of so far, with a temperature of about 40 Kelvin, or if you prefer, minus 391 degrees below zero. Wow, that's unimaginably cold. Let's take a look at the southern polar region of Triton. When Voyager 2 was flying by in 1989, Triton's southern pole was more or less pointed toward the sun. So the sun was warming Triton's southern hemisphere, although warming is a very relative term, but that was enough to generate these little black plumes that you see everywhere. These plumes are the result of geysers or cryovolcanoes, literally cold volcanoes. And there's winds blowing in Triton's very thin atmosphere, blowing these downrange. So we're starting to see a little bit of geologic activity going on inside Triton. There's volcanism, albeit cryovolcanism on Triton. And this does mean that Triton would have a very thin atmosphere, probably just surface ice that evaporates once it's warmed up by the sun. So earlier we talked about how moons can be classified as regular and irregular moons. That's one way of thinking about them. But there's a geologic classification that we can assign moons as well. Geologically active moons are those that have relatively few craters on the surface, so they have young surfaces, and this tells us that there's some source of internal heat that is constantly renewing their surfaces. Once active moons, such as Ganymede, Miranda at Uranus, and Mimas at Saturn, are moons that, well, as the name implies, shows previous geological activity, but nothing lately. Nothing really much has happened. And then finally, we have the never active moons, such as Callisto. These are moons that never became geologically active. As a result, they just formed and just kept taking hits after hits after hits. And that's it for the never active moons. By the way, there are two moons in this image that we haven't yet looked at. Let's take a brief look at them here. Here is Mimas on the left from Saturn, and Miranda at Uranus on the right. So both of these are clearly, there's some evidence of what's called tectonic fracturing. There are little lines that tell us that once upon a time was a period when the surfaces of these moons were kind of being pulled and stretched, and there was some activity, but then that activity shut down. And that makes sense. These moons are fairly small, and because they are far enough away from their home planets, they would not have really experienced much in the way of tidal heating. So these moons lose their heat and they shut down, and they just start taking crater hits ever since. And by the way, speaking of crater hits, Mimas clearly has taken one for the team. It's taken a very, very large hit at some point. So there's a whole geologic history of the outer solar system inscribed on the surfaces of these moons.